Welcome to our Engineers Newsletter live broadcast. Today, we'll discuss air handling systems from the perspective of energy reduction and indoor air quality. I'm Jeannie Harshoff from Trane System Engineering Department, and I'll be your host today. To cover this information today, we're delighted to have Art Hallstrom return to an E&L broadcast. Art is an ASHRAE Fellow and manager of Trane's Applied System Specialists. Also joining us today is John Murphy. John is an applications engineer and lead accredited professional. His primary responsibility is to help customers with the design and application of HVAC systems in buildings. And finally, Dennis Stanke. Dennis is a staff applications engineer and ASHRAE Fellow. Formerly chairman for the ASHRAE 62.1 Committee, Dennis serves on the U.S. GBC Lead Technical Advisory Group for Indoor Environmental Quality, and like John, helps customers with the design and application of HVAC systems in buildings. Now, before we start today, why do we talk so much about energy? Well, according to the National Renewable Energy Lab, buildings account for about 40% of the primary energy used in the U.S. Buildings use more energy than cars. Residential buildings account for about 22% of the energy used, and commercial buildings account for 18%. As far as end use goes, about 33% of the commercial building energy is used for heating, cooling, and ventilation. Now that's NREL data. The Energy Information Administration, on the other hand, says that HVAC accounted for about 51% of the energy used in commercial buildings in 2006. And an eSource study says 30% of commercial building energy is used by the HVAC system. So, buildings use 40% of the U.S. energy, and HVAC systems use between 30 and 50% of that energy. It's easy to understand why buildings and HVAC are major targets for national energy reduction efforts. With that as background, Art starts us out today with an update on some of the latest industry initiatives for measuring building environmental quality and energy use. Art, what lies ahead?
The information Jeannie just shared is very important. Buildings use more new energy than the transportation or industrial sectors. And as the #1 energy user segment, we can expect increasing focus on building energy reductions. Could we just close the outside air dampers to save energy? For a lot of reasons, the answer is no. Building owners should not let IAQ suffer to save energy. So what's the proper balance? ASHRAE is working on this issue. They just developed a building performance metrics publication. It defines how to measure a building's energy use, water use, thermal comfort, IAQ, lighting, and noise levels. Now, this new publication is needed and should be a must-read for building designers and owners. Once the building performance is known, the focus can switch to reducing energy use. Now, building energy use is commonly quantified as energy use intensity, or EUI for short. EUI is the building's total yearly energy use divided by the building area. It includes all energy sources: electric, oil, gas, etc. Now, every building has an EIU metric. It's similar to a car's miles per gallon. And like miles per gallon, EUI allows a building energy use to be compared with other buildings. Now, there are two common groups of energy-related rating methods. The first group measures environmental impact and energy. The second group, energy only. Now, Group 1 methods include LEED and the ASHRAE 189 Green Building Standards. Group 2 methods focus 100% on energy use. This group includes the EPA Energy Star program, the new ASHRAE Building Energy Quotient program, state standards like California's Title 24, and the European Union SIBSI label. The U.S. and international governments are using or are likely to use one of these methods for calculating, rating, and certifying building energy use. The Europe energy label is important since it is now a government-required label. Since 2006, any commercial building up for sale in the European Union must be assessed for energy usage and given an energy rating. The ASHRAE Building Energy Quotient, or Building EQ label, is the newest label. It was introduced at ASHRAE's June 2009 summer meeting. ASHRAE developed this label with international input and is currently in the pilot phase. Now, Building EQ provides a method to calculate and then grade the building's energy use at both the design condition and in operation. The as-designed rating relates to the estimated energy use. The as-operated rating is the actual energy used. As designed is similar to a car's EPA estimated gas mileage, whereas operated is similar to the car's actual mileage over time. In the case of a building, it's how much energy the building used over an average of 12 months. The Building EQ label lets an owner see how they're doing relative to the design and relative to other buildings like theirs. In this example, the building was designed as an A- building, but you can see it's being operated at the C level. One more point. EUI depends on where the energy use is measured. Site EUI is the electric and fossil fuel energy coming into the site. Source EUI is the site energy converted to source power using the EPA site-to-source energy conversion factors. Most EUI ratings are using source EUI today. How do the ASHRAE and EPA labels compare? The EPA on the bottom uses a statistical scale based on the energy use distribution in actual buildings. The 50% point means that the source EUI for the building equals the median EUI for that type of building. If it uses less energy than most similar buildings, a building achieves an EPA score greater than 50%. Any building that's better than 75% of the other similar buildings in the database can get the Energy Star Award. Note that even the best building designs can only score 100%, no matter how much less energy it uses. You can't do better than 100% on this scale, so there's no real incentive to greatly exceed the existing building stock. Now, the ASHRAE Building EQ letter ratings also tie to their EQ number ratings. If the EUI for a given building equals the EUI for the stock median building of that type, the building EQ number is 100 and it's a fair or a C building. The building EQ scale allows for more segmentation in the lower energy use area. A very good A- building uses less than half of the median for that type of building. On an EQ scale, an A+ or net zero building produces as much energy annually as it uses. Frankly, that's a pretty awesome building and off the scale for Energy Star Awards. My last slide shows the progression of code-intended energy standards towards the goal of net zero and why it's so important to know the year of any building rating method is referencing. The numbers on the left are from the ASHRAE EQ scale. Remember, 100 is the stock median. ASHRAE Standard 90.1 1999 provided a design that should use 10% less energy. This helps explain why it was widely adopted into codes. Each revision to 90.1 has lowered the building energy targets. A big drop is expected in the design EUI with the release of ASHRAE 90.1 2010 next year. Now, stretch goals push for lower energy use beyond the related 90.1 standard. LEED and the ASHRAE Advanced Energy Design Guides have stretch goals. Here you can see how LEED 2.1 energy points promoted lower energy use. LEED 2.2 referenced ASHRAE 90.1 2004, and the new LEED 2009 references ASHRAE 90.1 2007. I think you can easily see this ratcheting effect. Simply stated, it's getting harder to get energy-related stretch points. But in this broadcast, Dennis, John, and I will show you some ways to get those points.
Great information, Art. A lot of new things on the horizon for designers to consider. Great reasons to pay attention to air handling systems when designing to reduce energy and assure comfort and air quality. Now let's turn to Dennis Stanke for a detailed discussion of air handling system choices and the impact of these choices on energy usage. Dennis?
Buildings are built in all shapes and sizes, in all climates, for a wide variety of purposes. So it's no surprise that air handling systems come in many shapes and sizes too. It's hard to talk about energy impacts for all of the possible air handling systems all at once, so we've arranged our discussion today according to how systems are ventilated. But before we start, let's cover some energy-related strategies that apply to all ventilation systems. You can save energy by reducing airside pressure loss, by increasing fan efficiency, by recovering energy, or by using controls to coordinate and optimize operation. Starting with airside pressure loss, here's a news flash. Just like it takes energy to push a rock up a hill, it takes energy to move air through a duct. But how much energy? Well, that depends. For the rock, how fast do you want to move it, how hard do you plan to push, and how steep is the hill. For air, what's the airflow rate? How much pressure can the fan provide, and how steep is the system in terms of resistance to airflow? You all know fan curves. How much horsepower does it take for this FC fan to move 10,000 CFM through a given air system? Well, if the air handler and ducts are sized for, say, 2 inches total static pressure drop, the system curve might look like this. It takes 7 horsepower to deliver 10,000 CFM in this system, a pretty steep hill. But the air handler could be bigger, and filter and coil pressure drop could be reduced, and the ducts could use low-loss fittings. All of these would reduce the total static pressure that the fan sees. If total static pressure drops to 1.6 inches, it takes about 6 horsepower to deliver the same 10,000 CFM. A 20% drop in pressure cuts horsepower by 14%. It's like we push the same rock at the same speed, but the hill isn't as steep. On the other hand, what if we don't push the rock as fast? If we supply colder air and airflow drops to 8,000 CFM in the original duct, the results are more dramatic. With less airflow, the total static pressure drops to about 1.3 inches, and it takes about 3.5 horsepower to deliver 8,000 CFM. So a 20% airflow reduction cuts horsepower by 50%. Of course, if we reduce both duct pressure and airflow by 20%, we'd only need about 3 horsepower to deliver 8,000 CFM, a 57% fan energy savings. So if you have your choice, don't move as much air. It takes a lot less energy to supply low temperature air. On the other hand, if you can't reduce airflow, design the air system with less resistance so the fan doesn't need to push so hard. As a designer, you must decide. A small unit might have lower first cost, but it uses more fan horsepower, while a large unit costs more initially, but it uses less fan horsepower. What about fan efficiency? Well, that's important too. You have a lot of air handling system configurations and a lot of fan choices. Housed fans, forward curved or airfoil blades, belt drive or direct drive, plenum fans, and so on. Of course, you need to pick the right fan for the application, but we don't have time to go into all of that today. We do plan to talk about fans in detail in our next broadcast, so mark your calendar for March 24th, 2010. Next, John is going to tell us a little bit about recovering energy. John?
Exhaust air energy recovery can be applied to any system type, and energy codes are beginning to require it for more and more buildings. When it's hot and humid outside, a total energy wheel transfers sensible heat and moisture from the outdoor air to the cooler, drier exhaust air stream. This pre-cools and pre-dries the entering outdoor air, saving cooling energy. When it's cold outside, the wheel transfers sensible heat from the warmer exhaust air and uses to preheat the entering outdoor air. This saves heating energy. A side benefit is that total energy recovery also transfers moisture from the exhaust air to humidify the dry entering outdoor air. This can save energy if humidification equipment is being used. In humid or cold climates, using a total energy recovery device typically results in a greater potential for equipment downsizing and more energy savings than sensible recovery devices. Of course, this device adds pressure drop, which increases fan energy use and offsets some of that benefit. So it's important to analyze the savings for each project. Back to Dennis.
Finally, let's talk a little bit about controls. Factory-mounted, pre-engineered controls can save energy by reducing simultaneous heating and cooling, by optimizing operation, and so on. Consider demand-controlled ventilation. Let's say we have a 4,000 square foot lecture hall designed for 260 people. With design population in the zone, Standard 62 requires outdoor air at the rate of 7.5 CFM per person plus 0.06 CFM per square foot. That's about 2,200 CFM for this example lecture hall, and it takes about 4 tons to cool this much outdoor air on a hot day. But if the number of people drops, the zone doesn't need as much outdoor airflow. With 130 people, it only needs about 1,200 CFM, and it takes a little less than 2 tons to cool this much air. It seems obvious that you'd spend less energy on outdoor air conditioning if you could provide only current outdoor airflow required rather than simply providing design outdoor airflow at all conditions. Any control strategy that adjusts outdoor airflow in response to current ventilation requirements is called demand-controlled ventilation. It can be accomplished using different approaches, such as population estimates, occupancy sensors, and CO2 sensors. We don't have time to tell you about these in detail today, but earlier broadcasts have covered demand-controlled ventilation in detail, and we've written quite a bit about it, so you should be able to figure out how to do it. If you have trouble, call us or send us an email. We'll be glad to help. Incidentally, to comply with Standard 90.1, your design must use demand-controlled ventilation in high occupant density zones, defined as zones with more than 40 people per 1,000 square feet. So, we've discussed several examples of energy-saving approaches to consider for your next air handling system. You can save fan energy if you reduce supply airflow or reduce total static pressure. You can reduce outdoor air preconditioning with total energy recovery. You can use controls to avoid system fighting or to match outdoor air intake flow to the actual zone population, for example. Of course, everything has a trade-off. Features that reduce energy usage often increase air handling system first cost. You must decide what's most important for you and your customer. Now let's move on to discuss energy-saving strategies for specific types of air handling systems. ASHRAE Standard 62.1 includes requirements for 3 major ventilation systems: single-zone systems, which are usually constant volume, multiple-zone systems, which are usually VAV, and 100% outdoor air systems. Let's start with the simplest. In a single-zone system, one air handler serves one thermal zone with a mixture of outdoor air and recirculated air. Although you can design a single-zone VAV system, as John will explain, a constant volume fan is much more common for these systems. As sensible load in the zone changes, the thermostat modulates cooling capacity, which changes supply air temperature to maintain the dry bulb temperature in the zone at set point. The outdoor air intake flow is set to be equal to or greater than the minimum requirement for proper ventilation in the zone. Basic constant volume systems control humidity indirectly and not very well at part load because the supply air temperature is much warmer and wetter at part load than at design. So think about it carefully before using this kind of system in humid climates like New Orleans. Basic constant volume units control sensible temperature, but they don't control relative humidity, and they can use quite a bit of energy too. So John Murphy is going to show us some design approaches that can transform these simple units into high-performance systems.
While there are certainly other strategies, the three we'll focus on today are single zone VAV, split dehumidification units, and a series desiccant wheel. As Dennis mentioned earlier, a traditional single zone constant volume air handler uses a temperature sensor in the space to vary cooling capacity, and the supply fan delivers a constant quantity of air at all times. On the other hand, in a single zone VAV system, the temperature sensor in the space is used to directly vary the airflow delivered by the supply fan. Because the unit serves only one zone, no VAV terminals are needed. And like a conventional VAV system, cooling capacity is modulated to maintain a discharge air temperature at a set point. Now, compared to a constant volume air handler, single zone VAV systems result in fan energy savings at part load conditions, and typically less fan generated noise. It also improves dehumidification performance because the system continues to deliver cool, dry air at part load conditions. Of course, the air distribution system needs to be designed to accommodate variable airflow. So keep the ducts as short and symmetric as possible and use diffusers to prevent dumping at low airflows. Single zone VAV is an excellent system for large, densely occupied zones that have variable cooling loads. Common examples include gymnasiums, cafeterias, lecture halls, auditoriums, places of worship, and arenas. Now, because this system is often used for densely occupied zones with highly variable population, it's typically a good application for CO2-based demand control ventilation. As Dennis discussed, this reduces energy use by not over-ventilating the zone at partial occupancy. As part of this strategy, a flow measuring outdoor air damper can be used to document intake airflow and ensure that it doesn't drop below the ASHRAE standard 62.1 minimum requirement for the space. Finally, since demand control ventilation reduces intake airflow during partial occupancy, don't forget to provide some method to reduce exhaust airflow in order to control building pressure. One final comment about single zone VAV. Here's a recent change to ASHRAE standard 90.1. Effective January 1, 2010, any air handler that is equipped with a chill water cooling coil and a supply fan of 5 horsepower or larger must be operated by either a 2-speed motor or variable speed drive. Basically, this will require single zone VAV on larger air handlers. The next opportunity we'll discuss is to use a dual path air handler configuration. We sometimes refer to this as a split dehumidification unit. This approach separates indoor load from outdoor load, so energy isn't wasted on excessive cooling for dehumidification, followed by reheat. The outdoor and recirculated air paths each include a dedicated coil, but the same supply fan serves both air paths. The top coil dehumidifies just outdoor air, delivering it dry enough to also offset the space latent load. The lower coil provides additional cooling needed to offset the sensible load. To save footprint, one air path can be situated above the other by using a stacked air handler arrangement. A space humidity sensor is used to control the outdoor coil, and a space temperature sensor is used to control the capacity of the recirculated air coil. This dual path approach results in better dehumidification performance than a basic constant volume air handler, because the humid outdoor air continues to be dehumidified to a low dew point at part load, and is then mixed with the dry recirculated air. The footprint of the overall unit is smaller because the bottom cooling coil need only be sized for recirculated airflow, not the mixture of outdoor plus recirculated airflows. Of course, you could keep the same air handler footprint and lower fan energy. Since only recirculated air flows through the bottom cooling coil, the face velocity will be much lower than a single path unit of the same size. In non-arid climates, this is an excellent choice for larger zones where constant airflow is desired and humidity control is needed. Finally, for those applications that need drier supply air, consider equipping the air handler with a series Type 3 desiccant wheel. This concept places a special desiccant wheel in series with the cooling coil, with the regeneration side of the wheel upstream of the cooling coil and the process side downstream of the coil. You may have heard Trane refer to this technology as CDQ, which stands for cool, dry, and quiet. The desiccant wheel absorbs water vapor from the air downstream of the coil, enabling the system to deliver drier supply air, that is a lower dew point, without lowering the coil temperature. This absorption process does release a little bit of sensible heat, which warms the leaving air, but the resulting supply air is still cool and very dry. 55-degree dry bulb and 42-degree dew point in this example. When the wheel rotates, it releases the absorbed water vapor into the air upstream of the coil, and the cooling coil gets a second shot at removing this water vapor via condensation. And unlike a traditional desiccant dehumidification system, a separate regeneration airstream is not needed. Moisture transfer occurs within a single airstream. This configuration works because of the type of desiccant being used. The ability of this Type 3 desiccant to absorb water vapor depends on the relative humidity of the air going across its surface. Air leaving an active cooling coil is nearly saturated, with a relative humidity exceeding 95%. At this condition, the Type 3 desiccant can absorb lots of water vapor from the airstream. Now, because the relative humidity of the air upstream of the coil is lower than the RH downstream, the wheel rotates into the mixed airstream. Desiccant releases the water vapor to the air. Now, this chart shows the performance of this system in an example surgery room. Air leaves the cooling coil at a very high relative humidity, nearly saturated. The series desiccant wheel absorbs water vapor, drying the supply air to a dew point of 42 degrees, or about 40 grains per pound. Sensible heat added by the absorption process does raise the supply air dry bulb temperature a little bit to 55 degrees. Now, the wheel rotates back up in the mixed air stream, entering the regeneration side of the wheel. That air is less humid, about 40% in this example. At this relative humidity, the desiccant can no longer hold water vapor to absorb downstream of the cooling coil, so it's released to the mixed air stream, where it can then condense in the cooling coil as it goes through. Now, to deliver this same supply air condition, a traditional cool and reheat system, the cooling coil would need to cool the air to about 43 degrees in order to achieve the 42-degree dew point. And then the reheat coil must warm it back up to the 55-degree supply air dry bulb temperature. By contrast, a series Type 3 desiccant wheel can deliver the same supply air dew point using fewer tons, doesn't need to add the reheat, and it can achieve this lower supply air dew point with a warmer coil temperature, 51 degrees versus 43 degrees for the cool and reheat approach. Unlike a system with a cooling coil alone, the supply air dew point can be lower than the coil's surface temperature. This warmer coil enables more efficient mechanical cooling, either a higher suction temperature in DX equipment, or warmer water, or a lower flow rate in a chill water system. Basically, adding a series desiccant wheel changes the dehumidification performance of a traditional cooling coil, trading sensible capacity for more latent capacity. The latent or dehumidification capacity of the system increases while the total cooling capacity remains about the same. And as I mentioned earlier, the series configuration requires only one airstream. A separate exhaust airstream for regeneration is not needed. If the space needs independent control of both temperature and humidity, you should investigate the benefits of using a series Type 3 desiccant wheel when the required supply air dew point is below about 50 degrees. Common examples include surgery rooms, supermarkets, laboratories, pharmacies, libraries, museums, archive rooms, and many process applications.
Okay, we've covered constant volume single zone systems. Next we'll talk about multiple zone systems. We'll focus on VAV since they're the most common and offer many energy saving opportunities. For multiple zone systems in general, one air handler serves many zones with a mixture of outdoor air and recirculated air. Although these systems can use constant volume fans and terminal reheat, VAV systems are much more common. The air handling unit delivers supply air to all VAV boxes, and each VAV box adjusts its airflow so that the sensible capacity of the box matches the load in the zone, and the zone temperature matches the thermostat set point. A central fan, meanwhile, delivers the total quantity of outdoor air needed by all zones at a constant temperature, usually around 55 degrees. 55 degree supply air is usually dry enough to indirectly maintain a reasonable relative humidity level in each zone. As we've already seen, energy use in any air handling system can be reduced in many ways, including lowering airflow and pressure loss and recovering energy. But a key ingredient to make a VAV system truly high performance is the use of optimized system control strategies. We'll discuss a couple of those strategies today, starting with fan pressure optimization. In a VAV system, as the cooling load in each zone changes, each VAV box modulates to vary the airflow supplied to its zone. This causes the pressure inside the supply ductwork to change. The air handling unit modulates the supply fan airflow to maintain the duct static pressure at a set point. In many systems, the pressure sensor is located about 2/3 of the distance down the main supply duct. Although this is the traditionally recommended location, there's nothing magical about that distance. It usually results in adequate static pressure for design conditions. But at part load, when none of the boxes are wide open, the system still maintains the static pressure at set point, so it's higher than would actually be required to maintain box airflow in every zone. It's possible to optimize this static pressure control function to provide just enough pressure in the duct and minimize fan energy consumption, but it usually takes communicating controllers on the VAV boxes to do it. Each VAV box controller knows the current position of its damper. The building automation system continually polls these individual box controllers, looking for the one with the most open damper. The fan static pressure set point can be reset lower and lower until this particular VAV box is nearly wide open. During this process, total supply airflow remains constant because each box opens to maintain its required airflow, but static pressure in the supply duct is reduced. The result is that the supply fan generates only enough static pressure to push the required quantity of air through the critical VAV box. Standard 90.1 requires this fan pressure optimization approach in many VAV systems with DDC controls because it reduces supply fan energy use. At part load conditions, the supply fan operates at a lower static pressure than it would with traditional control where the static pressure set point is fixed at 1 inch, for instance. And as I showed earlier, lower fan static pressure means lower fan horsepower and less energy use. But fan pressure optimization offers several other benefits too. It reduces the risk of fan surge. By allowing the fan to operate at lower pressures when the zone loads require less supply airflow, the fan operating point is kept further away from the surge region than when using conventional duct pressure control. And lowering duct static lowers sound levels. Because the supply fan doesn't need to generate as much static pressure, it typically generates less noise. And with lower pressures in the supply ductwork, the dampers in the VAV boxes will be more open, resulting in lower air velocity and less noise generated at each box. Finally, this approach allows for flexible sensor location. Because fan pressure optimization uses the position of the VAV box dampers to reset the static pressure set point, the sensor can be located almost anywhere in the supply ductwork. The most convenient location is usually at or near the outlet of the air handling unit. In fact, the sensor can often be factory installed and tested. When it's located near the fan, the sensor can also serve as a high duct pressure sensor to help protect the ductwork from damage in the event of a fire damper closing. Okay, let's turn to another control option: ventilation optimization. In a typical VAV system, the air handling unit delivers a mixture of outdoor air and recirculated air to individually controlled zones. Ventilation systems are designed to bring in at least the minimum required outdoor airflow to properly ventilate all zones at the worst case condition. So at any other condition, the same intake airflow results in overventilation. Standard 62 permits the dynamic reset of outdoor airflow as operating conditions change. The goal of dynamic reset is to bring in only the minimum amount of outdoor air needed for the current operating condition, which saves energy. For a VAV system, one approach would be to install a CO2 sensor in every zone. This approach uses the building automation system to monitor all the sensors, determine how much outdoor airflow must be brought in at the air handler to satisfy all the zones, and then reposition the outdoor air damper accordingly. However, it's costly to use all of these CO2 sensors since they must be high quality to avoid frequent calibration or large ventilation errors. Besides, most zones in VAV systems are always somewhat overventilated, regardless of operating conditions. Why bear the expense of installing and maintaining sensors in all of those non-critical zones if most of them don't help control the system anyway? An alternative dynamic reset approach combines several demand-controlled ventilation technologies at the zone level with ventilation reset control at the system level. First, considering the zone level, CO2 sensors are installed only in those zones that are densely occupied and experience widely varying population. In this example, this means CO2 sensors are only used in the conference room and the lounge. These are the best zones for CO2 sensing since they offer the biggest potential for ventilation reduction. Zones that are less densely occupied and are frequently unoccupied during normal operation are probably better suited for occupancy sensors. Many zones in a typical office building fall into this category. In this example, each private office has an occupancy sensor to indicate when it's unoccupied and requires less outdoor airflow. Finally, all other zones, those that are sparsely populated or occupied at a constant level or in a predictable pattern, may be best suited for control using time-of-day scheduling in the building automation system. This schedule can simply indicate when the zone is expected to be occupied and ventilated for design population, or it can be used to vary zone ventilation requirements based on anticipated population level during each occupied hour. Of course, it's not always easy to predict hourly population levels, but it might be possible in some zones, such as classrooms or cafeterias. In any case, various zone-level demand-controlled ventilation approaches can be used to reset outdoor airflow requirement for each zone. In addition to resetting its zone outdoor airflow requirement, each VAV controller continuously monitors primary airflow being delivered to its zone. So the fraction of outdoor air currently required can be calculated for each zone. These zone-level ventilation requirements can be tied together in an overall ventilation reset strategy at the system level. The building automation system periodically gathers data from all the VAV zones and solves the multiple zone system equations defined in ASHRAE 62 to determine how much outdoor air must be introduced at the air handling unit to satisfy all of the zones served. Finally, the building automation system sends this newly calculated outdoor airflow set point to the air handling unit controller, which modulates the outdoor air damper to maintain this new set point. Of course, this requires an outdoor airflow sensor in the unit. By combining demand-controlled ventilation at the zone level with ventilation reset control at the system level, each zone receives at least its minimum required outdoor airflow. Ventilation optimization avoids both IAQ problems due to underventilation and energy waste due to overventilation. So system ventilation can be optimized without requiring a CO2 sensor in every zone. CO2 sensors are really only needed in those zones where they bring the most benefit. This minimizes installed cost, avoids the periodic calibration and cleaning required to assure proper sensor operation, and it also reduces the risk of overventilation due to faulty sensor readings. For most zones, occupancy sensors and time-of-day schedules can be used effectively to reset ventilation requirements. And this ventilation optimization strategy supports LEED EQ Credit 1, which requires CO2 sensors in densely occupied zones and outdoor air intake flow measurement to cover all other zones. And like fan pressure optimization, ventilation optimization is beneficial with single-path VAV or parallel fan-powered VAV. Actually, it's beneficial in any VAV system. Of course, the impact of any strategy on the operating cost of a building depends on climate, building usage, and utility costs. Designers need to make important first cost versus life cycle cost decisions on every job. Depending upon project budget pressures and long-term cost of ownership considerations, many projects may benefit by spending more for controls at the outset, since this money will be paid back quickly by operating cost savings. Building analysis tools like Energy Plus or Trane 700 can help with these decisions. They can be used to analyze different strategies and compare both energy saving and operating cost dollars. To illustrate, we use Trane 700 to model an office building and compare a conventional chilled water VAV system to a system that uses the optimized control strategies listed, including fan pressure and ventilation optimization approaches that I described. These results show that there is potential to save energy in VAV air handling systems by using optimized control strategies. The red column to the left for each city is the typical system, and the blue column to the right is the system with optimized controls. The y-axis is overall energy consumption, shown as a percentage of the base case. Just optimizing system control reduced HVAC energy by 9% for the building in Houston, 11% in Los Angeles, 17% in Philadelphia, and 18% in St. Louis. Another important strategy which lowers both airflow and energy usage even more is low temperature supply air. John can tell us all about it.
Delivering the supply air at a colder temperature allows the system to deliver a lower airflow rate. This can significantly reduce fan energy use. It can also allow fans, air handlers, and ductwork to be downsized, which reduces first cost. Another benefit is that in non-arid climates, delivering the air colder also results in delivering the air drier, which can lower indoor humidity levels. But while supplying air at a colder temperature reduces fan energy use, it can increase reheat energy and result in fewer hours when the airside economizer can provide all the necessary cooling. These impacts partially offset the fan energy savings. Therefore, intelligent system control is crucial to fully realize the potential energy savings of a low-temperature VAV system. For example, resetting the supply air temperature upward at part load helps maximize the benefit of the airside economizer and reduces reheat energy use. And since ASHRAE Standard 55 shows that people are comfortable at warmer temperatures if the humidity is lower, consider raising the space temperature set point by 1 or 2 degrees to further reduce airflow and fan energy use. Now, while I did say that you can downsize ducts to reduce first cost, if you want to maximize energy savings, consider designing the system for cold air, but keep the ductwork the same size as it would be for a 55-degree supply air. This further reduces fan energy and allows supply air temperature reset to be used in systems that serve zones with near constant cooling loads. Keeping the same size duct also improves the ability of the system to respond to any future increases in load, since it will be capable of handling an increased airflow rate if needed. Of course, cold air systems are not without challenges. Designers typically express 2 concerns with this approach: minimizing comfort issues related to cold air dumping on the occupants, and avoiding condensation on the components of the air distribution system. Now, a great resource for anyone designing a cold air system is this ASHRAE design guide. It discusses how to avoid these problems in detail. And Trane recently published a new application manual on chill water VAV systems that also discusses low temperature air. Both of these publications are listed in the bibliography for this broadcast. For example, nobody wants cold air dumping on their neck. That's why linear slot diffusers with a high induction ratio are a great idea for these systems. They induce large quantities of air from the space to mix with the cold supply air. So this mixture drops slowly into the space at virtually room temperature. On the other hand, Conventional diffusers can result in cold air dumping at reduced airflows. Another solution to avoid dumping is to use fan-powered VAV terminals to mix warm plenum air with cold primary air before it gets to the diffusers. In this example, the terminal mixes 80-degree air from the plenum with 45 degrees primary air to discharge 55-degree supply air to the diffusers. This approach can allow you to use diffusers with lower induction ratios, but these small terminal fans do consume energy. Now, either a series or a parallel fan-powered terminal can be used as an air blender. What's different for this application is that the fan in the parallel terminal is controlled to operate whenever the zone is occupied to provide this blending. Next, since the surfaces of the air distribution components in a low-temp system are colder than a conventional system, everyone worries about condensation on the diffusers or ductwork. How do you avoid it? Well, first, insulate all the cold surfaces. This includes supply ducts, VAV terminals, and diffusers. You should be doing this anyway to avoid wasting energy, but it's vital in a cold air system. But insulation alone cannot prevent condensation. A properly sealed vapor retarder must be included on the warm side of the insulation to prevent condensation within the insulation itself. Next, use an open sealing plenum return if possible. This results in a conditioned plenum, which means a lower dew point and less risk of condensation. During humid weather, maintain positive building pressurization to minimize the infiltration of humid outdoor air. Monitor indoor humidity during unoccupied periods and turn on the system if necessary to prevent the humidity from rising too high. And very important, during startup, after the system has been shut off, slowly ramp down the supply air temperature to gradually pull down the humidity in the building. And finally, along with this slow pull down, linear slot diffusers also help avoid condensation on the room side of diffusers by increasing air motion. As I mentioned, these and other recommendations are discussed in the ASHRAE Design Guide and the Trane Application Manual. Now, earlier, Dennis shared the results of a trace analysis that showed the potential to save energy in a VAV system just by using optimized airside controls. Now we'll build on that to compare a high-performance chill water VAV system to a typical system design. There's a slide in your handout that lists all the strategies implemented in this high-performance VAV system. For example, in addition to optimized controls, we used 48-degree supply air but kept the same size ductwork. We used high-efficiency chillers and high-efficiency fans. We see that the high-performance system reduced HVAC energy use by 53% for this building in Houston, 36% in Los Angeles, 55% in Philadelphia, and 54% in St. Louis. Now note that the savings is coming only from changes to the design and control of the HVAC system. There were no changes to the building envelope, no lighting or flood load reductions, and no cross-cutting strategies like shading or daylighting. For any real project, we'd strongly recommend that these other types of strategies are also investigated.
We've covered constant volume single zone and VAV multiple zone systems. Finally, we'll look at 100% or dedicated outdoor air systems and how to make them high performance. Once again, John Murphy will tell us all about it.
A dedicated outdoor air system uses a separate unit to condition all the outdoor air brought into the building for ventilation, and then delivers it either directly to the occupied spaces or to local HVAC units serving those spaces. Meanwhile, the local units in or near each space cool or heat recirculated air to maintain space temperature. Treating this outdoor air separately from recirculated air can help limit indoor humidity levels by dehumidifying this outdoor air to a dew point that's low enough to offset all the space latent load. This leaves the local HVAC units to handle only sensible cooling loads. Dedicated outdoor air systems are used with many different types of local HVAC units, such as fan coils, PTACs, water source heat pumps, DX splits, VRF, chilled beams, and even small package rooftops. They can also be used with floor-by-floor VAV air handlers or self-contained units. There's also a wide range of equipment types used for the dedicated outdoor air unit itself, from packaged DX units to specialty mechanical or desiccant dehumidifiers, or even chilled water air handlers. One of the primary differentiators between these choices is how dry they can deliver this air. The top part of this chart depicts the dew point that the dedicated outdoor air unit must deliver to maintain indoor humidity at either 60% or 50% RH. This is a range because ventilation rates and indoor latent loads vary by application. Note that this chart is based on the dedicated outdoor air system offsetting the entire indoor latent load, allowing the local units to run dry and provide only sensible cooling. The bottom part of this chart depicts the typical range of dew points that can be achieved by the various types of equipment. Packaged DX units may be capable of dehumidifying 100% outdoor air to dew points in the mid-50s. This may be okay for some applications if 60% RH is acceptable and the building doesn't have large indoor latent loads, or if you rely on the local units to handle some of the dehumidification. But for high-performance buildings where lower humidity levels are desired, they may not be able to deliver the air dry enough. This need for drier air often necessitates the use of specialty mechanical or desiccant dehumidifier, or even a chilled water air handler. What I want to discuss in this section is how you can use chilled water air handlers to deliver a high-performance dedicated outdoor air system. As shown in the previous slide, the first benefit of using chilled water for this application is that it's capable of delivering much drier air, lower dew points. Next, a chilled water air handler is more capable of operating over the wide operating envelope required of a dedicated outdoor unit. Because it sees 100% outdoor air, the air entering the cooling coil of a dedicated outdoor air unit ranges from hot and humid to warm to mild to even cold. As an example, this chart shows the daytime outdoor conditions for Nashville, Tennessee. Certainly a much broader range of entering coil conditions than a conventional mixed air system experiences. This wide operating envelope is a challenge for DX refrigeration system. Chilled water, however, is very capable of responding to wide ranges of conditions, partially because the water loop acts like a buffer. In addition, for high-performance buildings, many engineers consider implementing demand control ventilation to reduce outdoor airflow during partial occupancy. Now, this does add complexity to a dedicated outdoor air system. A VAV damper and a sensor are needed for each zone where DCV is used, plus a VFD is needed up in the dedicated outdoor air unit. But this strategy can further reduce energy use. It also creates another challenge for a DX refrigeration system. Not only does the DX evaporator see a wide range of entering conditions, now it also experiences varying airflow across the evaporator. In most cases, the DX equipment will use hot gas bypass to allow it to operate under these conditions, and that wastes energy. As I mentioned before, a chilled water cooling coil is very capable of dealing with varying airflow and a wide range of entering conditions. Another benefit of using chilled water for the dedicated outdoor unit is greater flexibility and an opportunity for even higher levels of efficiency. Air handlers typically offer many fan choices, air cleaning options, energy recovery devices, and dehumidification enhancements, such as the Type 3 desiccant wheel. In addition, they can often incorporate some means to measure airflow, which can ensure that the system doesn't overventilate and waste energy. Finally, since a chilled water loop is being used, it opens up the possibility of using ice storage to shift load and reduce energy costs. Next, with a chiller, you get ARI certified performance, so you're sure to get what you paid for. There's currently no ARI certification program for DX dedicated outdoor air units. Finally, using a chiller will typically result in a lower refrigerant charge than a DX unit. This can also help achieve LEED EA credit 4. Now, as an example, here's one air handler configuration that is being used for high-performance dedicated outdoor air systems. It combines a total energy wheel and a Type 3 desiccant dehumidification wheel. The total energy wheel preconditions the outdoor air by exchanging energy with the exhaust air stream, and the series desiccant wheel allows the unit to deliver very dry air efficiently. Now, to see what I mean by high performance, I'm going to use Trane's Climate Changer Configurator program to analyze the performance of this air handling configuration. Here's the dual wheel unit that I described, with a total energy wheel and the series desiccant wheel. Let's do an example selection. Let's say this unit delivers 8,000 CFM of outdoor air. And let's look at one of those very warm and humid days. So 8,000 CFM, let's look at maybe 83-degree dry bulb and let's say 133 grains per pound. This equates to about a 75-degree dew point. Now, of course, you likely cannot return all this air back to the unit as exhaust. Some air goes out local exhaust fans, while some leaks out due to building pressurization. So we'll say that we can only get 6,000 CFM of exhaust air back to the dedicated outdoor air unit. And since this is a high-performance building, we'll shoot for 50% indoor relative humidity. Now, since this is 100% outdoor air, we have no recirculated return air to this unit, so we'll enter 0 CFM here. So here we see this unit configuration with all the components laid out. For this example, let's assume we want to dehumidify the outdoor air to 45 grains per pound, which is about a 45-degree dew point. The program calculates the performance, and here we can see that this configuration supplies air at the desired dew point of 45 degrees at a dry bulb temperature of about 55 degrees. Now, as I mentioned earlier in the broadcast, one of the benefits of using this series Type 3 desiccant wheel is it can deliver air at this low dew point without having to lower the coil temperature. In this example, it can deliver 45-degree dew point with only having to make 51-degree air leaving the cooling coil. And it did this without having to add any heat to regenerate the desiccant. Let's step back a second and go look at this performance of this unit plotted in the psychrometric chart. Here we can see that the enthalpy wheel pre-cools and pre-dehumidifies the outdoor air, exchanging energy with the exhaust air stream. Then the air passes through the upstream side of the desiccant wheel, where it picks up moisture from the desiccant, through the cooling coil, where it's cooled and dehumidified to about 51 degrees, and then through the downstream side of the desiccant wheel, which absorbs moisture to further dehumidify the air to 45-degree dew point. Again, this process does release a little bit of sensible heat, but the resulting supply air is still cool and very dry. Delivering the dehumidified air at this cool temperature, rather than warming it back up to room neutral, is another benefit of this series configuration. Delivering the air cold reduces the required capacity of the local HVAC units, allowing them to be smaller, less expensive, and consume less energy. If you want to dig into this cold versus neutral issue further, I discussed it on our September 2007 broadcast. It's listed in the bibliography, as is an article on the subject. Now, compared to using a cooling coil alone, this configuration reduces the design load in the cooling coil by about 40%. It also avoids the need to reheat this overcooled air, and it did it with a warmer or higher coil temperature, which improves cooling efficiency. Now, as I just mentioned, though, dedicated outdoor air units have to deal with a wide range of conditions. So let's look at how this configuration performs at a part load condition, like a mild rainy day. Here we'll go up here and change the outdoor conditions to 65-degree dry bulb and raining, or 100% relative humidity. The program recalculates the performance, and we'll see that this unit can still supply the air at the desired 45-degree dew point, and still without having to add any heat to regenerate the desiccant. Now, to better understand how this can happen, let's go back to remind ourselves how the Type 3 desiccant works. As I mentioned, the ability to absorb water vapor depends on the relative humidity of the air going across its surface. Upstream of the cooling coil, the desiccant must be exposed to air that is a lower relative humidity, typically below about 70%, in order to release the water vapor and regenerate the desiccant to continue the cycle. On the mild rainy day in my example, the RH of the entering outdoor air was 100%. This would be too high to regenerate the desiccant. So one option would be to use a preheat coil to increase the dry bulb temperature of the entering outdoor air by about 12 degrees in this example. This lowers the relative humidity of the air, which would allow the desiccant to regenerate. Now, this modest amount of low temperature heat can often be recovered from the condensing process of a chiller or refrigeration equipment. However, in the case of the dual wheel unit, when high outdoor RH conditions occur, the total energy wheel transfers moisture from the outdoor air to the exhaust air stream. This lowers the relative humidity of the air before it enters the desiccant wheel, allowing it to release the water vapor and continue the cycle. In this configuration, the total energy wheel reduces and often eliminates the need to add regenerative preheat, even at this high RH condition. So this dual wheel configuration delivers high performance because how the components complement one another. Adding the series desiccant wheel changes the dehumidification performance of the conventional cooling coil, trading sensible capacity for more latent capacity, making it a better dehumidifier. And adding a total energy wheel avoids the need to add preheat on those mild, rainy days, which minimizes overall energy use. Of course, the total energy wheel also provides year-round benefits by preconditioning the outdoor air to save both cooling and heating energy. Another capability of this configuration is that it can be used for after-hours humidity control. If indoor humidity rises when the building is unoccupied, the unit can be operated with the recirculating damper open and the outdoor damper closed. The series wheel and cooling coil will then dehumidify air recirculated from the building, dry it out to keep the indoor humidity level low. Now, many of you have probably read about the ASHRAE headquarters building in Atlanta that was recently renovated. The building includes a dedicated outdoor air unit that uses this dual wheel configuration. The series desiccant wheel in this unit dehumidifies all the outdoor air to about 47-degree dew point and then delivers it to the spaces. In addition, many areas of the building use CO2 sensors and VAV terminals to reduce outdoor airflow delivered during partial occupancy. A variation of this dual wheel concept is to put the Type 3 desiccant wheel in a parallel configuration rather than in series with the cooling coil. Here, the desiccant wheel is regenerated by exhaust air leaving the building. The benefit of this approach is that the exhaust air is typically at a low enough RH to regenerate this desiccant without having to add any heat. However, the drawback is that in order for the desiccant wheel to regenerate and continue the cycle, it must have sufficient exhaust airflow coming back from the building. Any air that leaks out of the building due to positive building pressurization or air leaving through local exhaust fans decreases the airflow coming back to this central unit. And if demand control ventilation is used to reduce the intake airflow, the central exhaust airflow must also be reduced in order to avoid negative building pressure. For some applications, there may be little or no centralized exhaust airflow to regenerate the desiccant, which would render it ineffective. If this wheel is in the series configuration that I showed earlier, it's regenerated by the entering outdoor air, so it can still dehumidify even if there is little or no exhaust airflow. Now, we've primarily focused on reducing energy use, but indoor air quality is equally important in a high-performance building. So Art is going to shift gears and wrap up this broadcast with a discussion of air cleaning technologies used in air handling systems. Art?
Indoor air cleaning accomplishes 4 objectives. It helps keep the building and air handling equipment cleaner, specifically the coils, so they retain good heat transfer performance with time, and the fans, so their air moving efficiency is not degraded. Air cleaning is required by some standards and some codes. For example, ASHRAE Standard 170 requires MERV 14 filters in some hospital operating rooms. Some LEED credits require air cleaning. LEED NC gives 1 point if all air supplied to a zone passes through a MERV 13 or better filter. And properly applied air cleaning can reduce the level of biological contaminants, which results in better indoor spaces. So, what are we trying to remove? Airborne contaminants from both indoor and outdoor sources. ASHRAE defines air contaminants as either particles or gases. Particulate matter comes in all shapes and sizes and includes solids such as dust, fumes, and bioaerosols, and liquids such as mist and fog. We want to dilute or remove particles because they get things dirty. They can reduce visibility, and some of them, particularly the bioaerosols, can cause diseases, infection, and allergic reactions. Note that the bioaerosols are a special class of particles. They are airborne biological materials, including viruses, bacteria, pollen, and fungi spores. Although living organisms produce them, bioaerosols themselves do not have to be alive to cause allergic, toxic, or inflammatory responses. Gaseous contaminants can be divided into organic and inorganic types. Volatile organic compounds, known as VOCs, have attracted considerable attention in non-industrial environments. They are carbon-based vapors, usually emitted by indoor sources, such as solvents, paint, glue, cleaning products, carpeting, furniture, and so on. VOCs are one of the leading causes of complaints about perceived indoor air quality. Non-organic gases have both indoor and outdoor sources. Many are produced either directly or indirectly by combustion processes. We want to dilute or remove gases because they can be corrosive, smelly, irritating, and even toxic. We can divide air cleaning options into three groups according to the primary contaminants they remove. Particulate filters capture and hold particulates. ASHRAE Standard 52.2 uses minimum efficiency reporting value, or MERV ratings, to compare filter efficiencies. Filters with very high MERV ratings capture very small particles, including many biological contaminants. Electronically enhanced filters can boost filter efficiency, providing they don't produce ozone. Gaseous air cleaners can remove gases and vapors. Adsorbents like activated carbon and potassium permanganate impregnated alumina can capture and hold gas molecules until they get saturated. A photocatalytic process can be used to oxidize gases, converting them into water vapor and CO2. Now, this process is somewhat similar to the catalytic converter on your car, but instead of using the heat of the engine to activate the reaction, a photocatalytic reactor uses UV light. The bioaerosols seem to be growing in importance. Biological contaminants include viruses, bacteria, and fungi spores. They are particles, so if they get to the particulate filter, they can be captured, but many are also viable. They can be inactivated using UVC lights or photocatalysis. Particulate filters don't help much if the particles don't get to the filter. The size of the particle is important because it impacts how long it can stay in the air. This chart from ASHRAE shows the settling time for some particles. Note that viruses can take a long time to settle due to their very small size. Recent studies focus on how these very small particles get around in a viable state. Turning to gaseous air cleaning, adsorbents have been used for a long time, so we're not spending any time on them. Photocatalytic reactors, on the other hand, have been recently introduced. They use ultraviolet light and titanium dioxide to convert organic pollutants to CO2 and water. A photocatalytic air cleaning system is shown here, installed in an air handling unit. The system uses a MERV 13 filter or better, followed by a catalytic air cleaner, which consists of a titanium dioxide catalyst applied to a media that's exposed to the UV light. The catalytic air cleaner is only about 6 inches deep and has a very low pressure drop of about 3/100ths of an inch. The media has a projected life of 15 years. The catalyst is not consumed, and it does not load up like an impingement filter. The UV bulbs have an effective life of about 15 months and do not create any measurable ozone during normal operation. This picture shows the photocatalytic process. UV light strikes the titanium dioxide catalyst, creating hydroxyl radicals on the surface. These radicals are very strong oxidizers, stronger than chlorine or ozone. As air passes over the catalyst, the hydroxyl radicals contact, and immediately react with the volatile organic compounds. This is a chemical reaction that oxidizes VOCs into carbon dioxide and water. The hydroxyl radicals also interact with the biological contaminants on contact, effectively inactivating them. This video illustrates how the catalytic air cleaner works. We have air in the space with large and small particles shown as black dots. Odors and VOCs are shown as orange dots, and biological contaminants like bacteria, viruses, mold spores are shown as red dots. Inside the air handler is a MERV-rated impingement filter, followed by the coil, and then the catalytic air cleaner. The fan can be anywhere in the air handling unit. Placing the air cleaner as shown downstream of the cooling coil is a good idea since the UV lights can do double duty. They power the photocatalytic oxidation and can also help to deactivate any microorganisms on the coil or drain pan surfaces. So let's turn on the fan. The larger black dots will collect on the particulate filter, but some get through. How many? This depends on the MERV level and the amount of filter rack bypass. The orange VOC dots are not reduced. Some of the red biological dots are captured by the impingement filter, but many get through. Next, we're going to increase the MERV level of the particulate filter. Making it a high MERV level filter stops more of the black dot particles. But notice the gases and the biologicals are still getting through. Now let's turn on the catalytic air cleaner. Some orange VOC dots now get converted into water vapor and CO2, and some red biological dots turn green, indicating they have been deactivated. Actual air cleaner performance depends on the size, type, and quantity of the contaminants. Effectiveness of the photocatalytic process can be increased by either slowing the air down or adding catalytic devices in series. One key to an effective catalytic process is getting even and sufficient intensity of the UV energy to the catalyst. Some designs, like the one on the left, had the UV bulb outside of the media. In this position, the bulb does not activate all of the media. In the design on the right, the UV bulbs are placed in the middle of the media to light up nearly all of the catalyst surface. As a result, fewer contaminants bypass the active surfaces, so that the process is much more effective. In summary, air cleaning is a complex issue, but it's getting easier to understand and control. It's best to know the contaminants of concern and where they're coming from. Have a goal in mind. Consider all of the available technologies and understand the maintenance requirements. Evaluate from an effectiveness and a total cost of ownership perspective.
Well, that brings us to the end of today's program. Now we know that energy reduction is important, and even greater emphasis will be placed on energy reduction in the future. Since air handling and HVAC systems are vital for IAQ and comfort, and since they account for a large portion of building energy use, energy-efficient air handling systems are a must. In quick summary, we showed that any system uses less energy if it moves less air, if it recovers heat, or if it uses controls wisely. Single-zone air handling systems can be configured to better match system capacity to both sensible and latent load, and thereby use less energy. Multiple zone VAV systems can use a variety of control approaches to optimize operation and reduce energy use. Today we discussed fan pressure and ventilation optimization. And low temperature air can significantly reduce fan energy use. 100% outdoor air systems with Type 3 desiccant wheels combined with traditional total energy recovery wheels lower indoor dew points without the energy penalty associated with very cold coils and reheat. And finally, air cleaning can be both effective and energy friendly if the right technology is selected for the job. The overall lesson: don't ignore air handling system energy saving opportunities. Remember that the energy needed to move air in buildings can be reduced significantly. Now, there are a number of publications available that provide more information on the material covered today, including several engineers' newsletters, application manuals, numerous articles, and a recently released engineering bulletin. A bibliography detailing these resources is available from your local site coordinator. Additionally, past broadcasts are available to order on Trane.com. So please check out the website for information on specific broadcasts. Thanks for joining us today. We'll look forward to seeing you next year.